You will recall from Part 1, we stated that stability is the tendency of a vessel to return to its original position after it has been inclined due to external forces. We also saw that it was possible to determine the stability of a vessel by locating 2 points in the vessel, the center of gravity and the center of buoyancy. We defined the center of gravity as that point in a vessel where all of the vertically downward forces of weight appear to act. We defined the center of buoyancy as that point in a vessel where all of the vertically upward forces of support or buoyancy can be considered to act. We also said that the center of buoyancy is the center of volume of the immersed portion of the hull. Displacement is the weight of water displaced by a floating object, and displacement is equal to the weight of the object itself. Further, we learned that the transverse metacenter, which is abbreviated as M, is that point to which the center of gravity, G, may rise and still permit the vessel to have positive stability. M is the intersection of the ZB2 line and the KG line. Remember, when a vessel is heeled, B, or the center of buoyancy, will move, and it will move towards the low side of the vessel. G, the center of gravity, will remain fixed. We define metacentric height, or GM, as the distance from G to M. And we said that metacentric height was a measure of a vessel's initial stability. And finally, we said that where M is above G, we have stable equilibrium or positive stability. When M is at G, we have neutral equilibrium. We also said that where G is above M, we have negative stability and an upsetting tendency. If you did not do well in the first examination in the study guide, replay and study Part 1 again. A lot of the material from Part 1 will be needed to understand what we'll cover in Part 2. In discussing the position of a vessel's center of gravity, we have assumed that everything in the vessel was fixed in position within the vessel. For all solid materials, this is true, unless the materials are free to roll around with the motion of the vessel. It should be obvious that where we have partially filled tanks containing water or fuel, there will be a movement of this liquid as the vessel or rig is inclined. When the liquid in a partially filled tank is free to move in this manner, we say that the tank has free surface. The effect of this movement is to make the ship behave as if the center of gravity were higher and GM were less than had been calculated for the upright, stable condition. The apparent movement of the tank center of gravity to a higher position due to free surface is called a virtual or imaginary rise of G, and its effect is to raise the center of gravity of the entire vessel. Let's take a look. Here we have a vessel in an upright position where the center of gravity is indicated by a capital letter G. We have a partially filled tank, and the center of gravity of the liquid in this tank is indicated by little g. When the vessel is inclined, the center of gravity of the liquid will shift to little g2. For reasons that are beyond the scope of this discussion, the net effect of this movement of little g upon the vessel's stability is an apparent movement of the center of gravity of the entire vessel, or G1, to the higher location of G2, shown here. The amount of this rise depends first on the dimensions of the surface of the liquid and the displacement of the vessel. The wider the tank, the greater the effect. Also, the greater the displacement, the less free surface will affect the position of G. And secondly, the specific gravity of the liquid will also have an effect. Fuel oil will have less effect than water, which in turn will not raise kg as much as a tank of drilling mud. You might be surprised to find out that free surface does not depend on how much liquid is in the tank. When the tank is empty, there is, of course, no free surface effect. Once you start to fill the tank, the free surface effect increases rapidly with the first few tons introduced and is nearly at its maximum value when the tank is about 5% full. It remains close to the maximum value until the tank is 95% full. Then it returns rapidly to zero for a full tank. The maximum free surface figure is tabulated for each tank on the vessel by the naval architects when the vessel is being designed. It is important to remember that the free surface correction for all slack tanks must be included in the calculation of kg for initial stability. The best example of how stability affects a vessel's behavior is found in the rolling period. The rolling period is the amount of time the vessel takes to move from an inclined position on one side all the way over to the end of the roll on the other side, and then back to the starting point on the first side. A comfortable rolling period will be between 15 to 30 seconds. It can be roughly calculated even before putting to sea by using the formula T equals 0.44b over the square root of gm, where T is the rolling period in seconds, B is the beam of the vessel in feet, and gm is, of course, the metacentric height. It should be apparent from the formula that a beamy or wide ship will have a slower roll than a narrow ship such as a destroyer. Also, a ship with a very large GM will be more rapid and uncomfortable in its motion than one with a small GM. Turning the formula inside out, we find that GM equals 0.44b over T squared. We can use this version of the formula to calculate GM after we have timed the roll, and then we can compare this with the figures we get when we compute GM as we did earlier in Part 1. This is a good check on the accuracy of our calculations. You must understand that the two formulas we have just discussed apply to ships of standard form only. They cannot be used to calculate the rolling period of a semi-submersible where the GM is known, nor can they be used to calculate the GM of a semi when its rolling period is known. The important thing to bear in mind is that an excessively long rolling period can indicate a dangerously small GM. In Part 1, we discussed the center of buoyancy, B, and the center of gravity, G, and we described how they must be in vertical alignment for the ship to be in stable condition when it's upright. If G is not directly above B, the ship will list toward the side that G is on. The same is true when we look at the vessel from the side. If G isn't directly above B on the center line from a thwartship or sideways, the ship will not sit flat in the water. In other words, it will not be on an even keel. Instead, it will trim until B moves under G to establish equilibrium. The draft of a vessel is the distance that it is submerged in the water, or the depth from the bottom of the keel to the water line. Draft marks are painted on both sides of a vessel, at the bow and also at the stern, in the following manner. The numbers are 6 inches high, with 6 inches space between them. The bottom of each number rests on an even foot of draft. This system of marking enables us to eyeball a vessel's draft with a high degree of accuracy. Trim is the difference in drafts fore and aft. If the vessel is deeper in the water forward, she is said to be trimmed by the head. If she is deeper in the water aft, she is said to be trimmed by the stern. To find the change in trim for any loading or unloading operation, we simply note the trim before and after the operation and combine them according to these rules. If both trims are toward the same end, subtract the smaller from the larger. If the trims are different, add them. Here are some examples. If the initial drafts are 9 feet forward and 13 feet aft, the rig or ship is trimmed 4 feet by the stern. After a transfer of ballast, if the drafts are 10 feet forward and 12 feet aft, we have a trim of 2 feet by the stern. So, the change in trim is the difference between the first and the second trim, or in this case, 2 feet. In our second problem, we have an initial draft of 18 feet forward and 16 feet aft, giving us a trim of 2 feet by the head. If, after loading, the draft becomes 24 feet forward and 25 feet aft, we get a trim of 1 foot by the stern. The trim has changed from by the head to by the stern, so we add the 2 trims, 2 feet and 1 foot, to obtain a change of trim of 3 feet. In problem 3, we have drafts of 19 feet forward and 21 feet 6 inches aft. So the vessel is trimmed 2 feet 6 inches by the stern. After loading, we observe the draft to be 21 feet forward and 23 feet aft. The ship is now trimmed 2 feet by the stern. Both trims are by the stern, so we subtract them to obtain a change of trim of 6 inches. In our last example, we have an initial draft of 15 feet forward and 15 feet 7 inches aft, giving us a trim of 7 inches by the stern. After loading, we read drafts of 16 feet 5 inches forward and 17 feet aft, a trim of 7 inches by the stern. The ship is trimmed evenly during loading, resulting in no change in trim. Even before we load or discharge cargo, equipment, fuel, or any other weight, we can calculate what effect the operation will have on the vessel's trim. To do this, we use our old friend moments. Whenever a weight is moved through a distance, a moment is produced. When anything is loaded or discharged on a vessel, moments are created. The ship reacts to these moments by trimming, by the bow or by the stern. Also, a new buoyancy force is set up which compensates for the additional moments. The ship trims about its tipping center, also called the center of flotation. The position of the tipping center changes for a given vessel with changes in draft, but the designer has made it easy for us to locate its position at any draft by use of the hydrostatic curves, which we discussed briefly in Part 1. A reproduction of the hydrostatic curves of the SEDCO 445 can be found on page 12 of your SEDCO self-study guide. The force which is causing the vessel to trim about this tipping center is called the trimming moment. In loading or discharging, this moment is determined by multiplying the weight of the material times the horizontal distance from the tipping center to its stowed position. We use a similar procedure when we shift cargo or equipment that is already on board. In this case, we multiply the weight moved times the distance moved, forward or aft, to obtain the trimming moments. The amount of change in trim that these moments will produce in any given situation can be calculated with the aid of a graph provided by the designer. The MT1, or moments to trim 1 inch, can be determined from either the deadweight scale or the hydrostatic curves. For a given vessel, the MT1 will be different at different drafts because of the change in waterplane shape and size. So, after first determining the mean draft, we go to the deadweight scale or hydrostatic curves and pick off the corresponding MT1. For the average small ship, MT1 will be in the neighborhood of 1,000 foot-tons per inch of trim. This means that if we load about 1,000 tons 1 foot forward of the tipping center, the vessel would change its trim by about 1 inch by the head. The 1,000 tons would also change the draft, of course. To determine this change of draft, we again go to the deadweight scale and determine the tons per inch immersion, or TPI, for the draft we are starting with. Now, the TPI is nothing more than the number of tons necessary to change the mean draft of a vessel 1 inch. For a moderate-sized vessel, we could expect it to be somewhere around 50 TPI. Now, let's do a full-scale example to help understand these two terms. Take a vessel with drafts of 21 feet forward and 19 feet aft. The average of these two drafts is the mean draft. It is 19 feet plus 21 feet divided by 2, which equals 20 feet. So 20 feet is the mean draft, which we use to enter the deadweight scale or hydrostatic curves to obtain the tons per inch immersion and the MT1 moments to trim 1 inch. For the purpose of this problem, assume that after consulting the deadweight scale or hydrostatic curves, we find that the MT1 for a mean draft of 20 feet is 1,000 tons per inch. Now, if we shift weights without adding or removing weight, we will change only the trim without changing the draft. In our problem, if we shift 500 tons of cargo from a forward location 100 feet aft to another location, we would produce a moment of 50,000 foot-tons. Divide this by an MT1 of 1,000 foot-tons per inch, and we obtain a change of trim of 50 inches. This 50-inch change will be divided equally between the bow and the stern. In other words, the bow will rise 25 inches and the stern will submerge 25 inches. Applying these amounts to the original draft, we get a final forward draft of 21 feet minus 2 feet 1 inch, or 18 feet 11 inches, and a final draft aft of 19 feet plus 2 feet 1 inch, or 21 feet 1 inch. Notice that the draft did not change because we didn't add or discharge weight. Now let's consider a case where we do change the draft by increasing or decreasing weight. Take a vessel with a forward draft of 15 feet and an after draft of 13 feet. The mean draft is an average of the two, or 14 feet. If, after examining the deadweight scale, we determine the TPI for a 14-foot mean draft to be 40 tons per inch, and if we load 60 tons 200 feet forward of the tipping center and 100 tons 50 feet aft of the tipping center, what will our final drafts be? The final mean draft will be the original mean draft plus, for loading, the added weight divided by the TPI, or tons per inch immersion. The added weight is 160 tons, and this is divided by 40, the TPI, which gives us 4 inches additional draft due to loading. So the final mean draft is 14 feet 4 inches. Now we would go to the deadweight scale and get the MT1. Let's assume in this problem that MT1 for a mean draft of 14 feet 4 inches is 1,000 foot-tons per inch of trim. Since we loaded 60 tons 200 feet forward of the tipping center, we have a positive moment of 12,000 foot-tons. Now, since we loaded 100 tons 50 feet aft of the tipping center, we have a negative trimming moment of 5,000 foot-tons. Combining these two, we obtain a net trimming moment of plus 7,000 foot-tons towards the bow. If we divide the 7,000 foot-tons by 1,000 foot-tons per inch, we have a final change of trim of 7 inches by the head. Note that this is a change of trim from the original trim. So what are the final drafts and the final trim? The initial forward draft was 15 feet. This was increased 4 inches by loading cargo to 15 feet 4 inches. It was further increased by half of the change of trim, or 3.5 inches, to 15 feet 7.5 inches. This is the final forward draft. The aft draft started at 13 feet and increased 4 inches due to added cargo, and decreased 3.5 inches due to change in trim, for a final draft of 13 feet and 1/2 inch. The mean of these two final drafts is 14 feet 4 inches, which agrees with our earlier finding for final mean draft and is a good check. Now, this type of problem is almost certain to appear on your license exam, so be sure to practice it until you are confident that you understand it completely. Well, we've covered quite a lot of material up to this point, so why don't we take a coffee break for 10 minutes or so,